Hello Nicholas, in this video we're going to be going through our OCR Combined Science Higher Paper for Chemistry Paper 1, and this is our predicted paper for 2024. So if you haven't had a go at this paper already, what we want you to do is to pause after the question comes up, have a go at it yourself on a bit of paper, you don't have to have printed it anything else, and then play the video and watch Charlotte work through the answers. Have you picked up on the right command words? Have you put everything into the answer you need to get all of the marks? And then move on to the next question. You can give yourself a grade at the end, you can give yourself a mark if you want to, but please use this to work out what you need to improve on for your exams. Good luck with everything.
Here we're told that the melting point of nitrogen is minus 210 degrees C and the boiling point of nitrogen is minus 196 degrees C. Here we're asked to predict the state of nitrogen at minus 125. So let's just visualise this here. So we know that the boiling point of nitrogen is minus 196 degrees C. Now that there is the temperature at which we're going to change from a liquid to a gas. We're also told that the melting point of nitrogen is minus 210. Now that is when we change from a solid and we melt to become a liquid. And we know that temperature is minus 210 degrees C. Well, here in this question, we're asking about the temperature minus 125 degrees C. So really what this question is testing us on is our negative numbers. So we need to know that minus 125 is going to be the highest out of all of these temperatures. And this means that we are a gas. And that's because we're looking at a temperature minus 125, which is warmer than the boiling point of nitrogen, which means it would have been enough energy there for it to boil. So it's a gas. The answer here is A. Methanol has a formula CH3OH, and it is a liquid at room temperature. Here we're asked to identify what type of substance methanol is. So methanol is a molecule. It just exists as one carbon, 4 hydrogens and an oxygen. There is no repeating structure to methanol. It is simply this standalone molecule. And the fact it's a liquid at room temperature means that it has a relatively low boiling point and melting point. We can also see here that it's made up only non-metals. And when we have something made of non-metals, that tells us that it has covalent bonding within its structure. And there's 2 structures that are composed of covalent bonds. That is simple molecules and giant covalent structures. So straight away that does narrow us down here. So if we think about what we actually know about simple molecules and giant covalent structures, we know that simple molecules always have a very low melting and boiling point. Whereas on the other side of things, the giant covalent structures always have a really very high melting and boiling point. Now that alone tells us that because it's a liquid at room temperature, we must have this simple molecule here. So the answer to this is A, simple molecule. In the modern periodic table, elements are arranged in order of their... Now this question is all about recall, isn't it? This is a fact that we're expected to know. So the answer to this is B, atomic number. Remember that periodic table arranges elements in order of their atomic number. If you don't already know that, that's a great fact to learn. Easy marks. Now we're asked to identify the formula of aluminium sulfate. Now to do this, we need to know 2 things. We need to know the charge on the aluminium ion and the charge on the sulfate ion. Well, to find the charge on aluminium, they would really expect you to use your periodic table. So if you go have a look on your periodic table now, you will see that aluminium is in group 3. Now because it's in group 3 and it has 3 electrons in its outer shell, it's going to form Al3+ charged ions. Now, sulfate, on the other hand, is something we just need to know off by heart because we can't find sulfate in the periodic table. Sulfate is SO4 with a charge of 2-. Now, straight away here, looking at the multiple choice options, I can eliminate A because it doesn't have that sulfate ion. That actually says aluminium sulfide if it was balanced. Now here though, I can see I have a 3+ charge on the aluminium, but a 2- charge on the sulfate. So what we want to do here is to balance these charges, and the easiest way to do this is essentially by crossing them over. We have Al2 and then SO4 with a little 3 down here. So see, all I've done there is essentially pull down the numbers of those charges and cross them over to the opposite side here. Now, the reason why this works is because we want to get the same amount of positive charge as we have negative charge. And we have 3+ and 2-. Now, the common charge that they could have would be 6+ and 6-. And we get that by timesing the Al 3+ by 2, which is what we've done here. And we get that by multiplying the SO4 2- by 3. And that's where we get this SO4 with the brackets and the 3 there. Now notice I haven't bothered to write the charges anymore. That's because they balance and cancel out essentially. So we don't need to write them down anymore. So looking at the multiple choice options, I can see that the answer here is going to be D. So D is my answer. So now we're told that there are many different models that can be used to represent a covalently bonded substance. However, they do not all provide the same information. Here we're asked to identify the model that does not show the bonding in a molecule. Dot and cross diagrams do show where bonding is. The overlapping circles and the shared pair of electrons all represent a covalent bond that's been formed. A ball and stick model is a 3D representation involving balls and sticks, essentially like this, but 3D, and each stick does represent a bond, a covalent bond. The 2D representations will look something along these lines, and again, every little stick that we draw here is going to represent a covalent bond. And then finally, we're just left with the chemical formula, so something a bit like CH4. Now see there, there's no indication of the bonding. We don't know there if the hydrogens are attached to each other or to the carbon, so we don't have information about bonding in the chemical formula. So the answer to this is D. Here we're asked to identify the correct half equation for the reaction occurring at the anode during the electrolysis of acidified water. So we're given 4 options here. Now, first and foremost, in a perfect world, you would have memorised this half equation. You will just know it. But because this is a multiple choice question, we can work this out. Let's not forget that an anode is a positive electrode. So we know that if we have a positive electrode, then the negatively charged ions are going to be attracted to it. So for that reason, if we look at all of these equations, we're going to expect to see a negatively charged ion giving away some electrons to the anode. We certainly wouldn't expect a positive ion to be going towards the anode. That wouldn't happen because positive and positive would end up repelling each other, whereas this negatively charged hydroxide ion will get attracted towards the anode. And for that reason alone, I can identify that A is going to be my answer. However, they do expect us to know that equation as well. So if you're not familiar with that, then it's a good opportunity to get revising it. The empirical formula of a substance is CH2O. The relative formula mass of the substance is 180. Work out the molecular formula of the substance. So here, what we need to do is to first remember what an empirical formula actually is. Now, the empirical formula tells us the simplest whole number ratio of atoms in a molecule. So that means it could be any scaled up version for the actual molecular formula. To work this out, the best thing to do would be to first work out the molecular mass of the empirical formula. So remember, if we don't know these numbers, we can go to the periodic table to get these mass numbers. So carbon is 12, we have 2 hydrogens, so 2 times 1, and then plus 16 for the oxygen. That gives us 30 for the molecular mass of this empirical formula. However, now we need to ask ourselves, well, how many of these empirical formulas then, with a mass of 30, fit into the molecular mass of 180? So here we've got 180 divided by 30, and we get 6, which tells us that there's 6 times the number of atoms that we have in that empirical formula. So we have C6H12O6. So the answer here is D. Sodium reacts with water in the following reaction. 2Na plus 2H2O goes to 2NaOH plus H2. We're told here that 25 grams of the sodium hydroxide is made, and we're asked to calculate the minimum mass of sodium required to make this. Now, if this ever came up in an exam, you don't have time to sit around and wait, I'm afraid. The way that I always like to start it is by writing the formula and then writing any information that I know underneath. So we don't need to know stuff about everything though. If we read the question, you can see that we were told some information about the sodium hydroxide and we're being asked about the sodium. So that's all that we care about here. So next up, I would do 3 rows, one for mass, one for the MR and one for the moles. So I know that we have 25 grams of sodium hydroxide. I can also use the periodic table to say, okay, sodium has a mass of 23 or an MR of 23. I can fill that in here. I know that oxygen is 16 and hydrogen is 1. So the MR of NaOH will be 23 plus 16 plus 1. That gives us 40. So now we can easily work out the moles of sodium hydroxide simply by saying moles is mass over the MR, and so 25 over 40. And that gives me an answer of 0.625. So now that I have the moles of sodium hydroxide, I can compare to the sodium in the equation, and I can see that that's a 2 to 2 or a 1 to 1 ratio between them. So that means that I have 0.625 moles of the sodium there, the same amount of moles as I had of sodium hydroxide. Finally, I can get the mass now of the sodium by saying that mass equals Mr. moles, MR times by the moles. So I'm going to do 23 times by 0.625. And that gives me the final answer, which is B, 14.375. Here we're asked to identify which of the following statement correctly describes a gas. So the first statement is it can be compressed. Well, gases can be compressed. You can make those particles closer together and turn it into a compressed gas. So that one is already correct. If we were short on time, we could just put an A in the box and be done. But as we're here together now, let's take a bit of time just to look through B, C and D and explain why it's not those. So B states that it has a fixed volume but no fixed shape. Well, actually gases don't have a fixed volume. They can fill whatever space they are in, and so that means that their volume can grow essentially. It's not like a liquid where they do indeed have a fixed volume and no fixed shape. You know, the shape fills a container with a liquid, doesn't it? But the volume always stays the same. So B is actually describing a liquid. Next up C, it says it cannot flow. And a lot of people here could get confused because they could associate the word flow with just liquids. But actually both gases and liquids can flow. The only substance that can't flow would be a solid. So C is actually describing a solid. Finally for D, a fixed volume and a fixed shape. Again, that there's just describing a solid. So here, hopefully you can see that even if A didn't jump out at you straight away as the answer, by identifying the other ones, you can also get your answer in the end as well. So here we've got A as our answer. Now we're asked to identify which of the following is an example of a chemical change. So to answer this, it's worthwhile recapping what a chemical change actually is. And in a chemical change, we have a chemical reaction occurring and new products forming. Whereas with a physical change, the matter may change state or its form, but it's still the same chemical. So here in this case, if we have a look through A, B, C and D, we'll be able to identify where we have a chemical change. Now the evaporation of water is just taking liquid water and changing it to gaseous water. We don't really have any new products, we still have H2O, don't we? So all that we have in A is an example of a physical change, so we can eliminate that. Now for B, we're looking at nitrogen and hydrogen forming ammonia. So to remind ourselves of the equation, that is N2 plus 3H2 goes to 2NH3. Don't have to write that, but I just have. So here I can clearly see that a chemical reaction has taken place and we have a new product. Now that tells us that B is correct. B is an example of a chemical change because we have fit those rules. However, if we look at the others too, just to eliminate those, C is the separation of oxygen from the air. Again, we're just separating things there. There's no chemical reaction occurring at all. And then for D, the melting of ice, that's very similar to the evaporation of water. We have there as a state change from solid H2O to liquid H2O. So we don't have a chemical change happening there either. So we are happy now, 100% sure that B is our answer. Here we are told that calcium reacts with oxygen to form calcium oxide. We're told that calcium is a metal. And we're asked in this question to describe how the position of calcium on the periodic table tells us that it is a metal. So here, this is a little bit of knowledge that you're expected to know about the periodic table. So we find metals over on the left-hand side of the periodic table, whereas the non-metals are found over on the right-hand side. So if you were to look at a periodic table, look for calcium, which is in group 2, you can see that it is indeed on the left-hand side of the periodic table. Okay, so for part B, we're told that the electronic structure of calcium is 2882. And we're asked to complete the diagram below to show the electronic structure of oxygen. So if we were to look at the periodic table of oxygen, we would see that down at the bottom we have an 8 and on the top we have 16. Now that number on the top is the mass number, or the atomic mass of the oxygen, whereas the 8 is the proton number, or the atomic number of oxygen. Now, what it's important that we know is that if we have an atom, then the number of the protons is equal to the number of the electrons. So that means that we know then that oxygen has 8 electrons in total. Now for electronic structure in the first shell of an atom, we can have 2 electrons. Whereas in subsequent shells, we can fit as many as 8 electrons. So we have 8 electrons to play with, we put 2 in the first shell, and that leaves us with 6 electrons left to fit into oxygen's outer shell. And that in total, you can see, gives us 8 electrons. So that there is the electronic structure of oxygen in diagram form. If we were to write it in a similar way to how calcium's was, we'd write it as 2, 6. So that there shows 2 different ways in which we can write down the electronic structure of oxygen, but of course they wanted us to draw it using the shells, which is why they gave us the diagram here. So in part C here, we're given the reaction between calcium and oxygen. We're told that 2 calciums react with oxygen to make 2 CaO. And here we're told to describe in terms of electron transfer what happens when calcium reacts with oxygen. So this is a 4 marker, but actually it's not going to take much to acquire those marks. Really, we need to understand what is happening to calcium and oxygen in terms of losing and gaining electrons. So, calcium, as we know that it has the electronic structure of 2882, you can see that it has 2 electrons in its outer shell. So 2 electrons in its outer shell means that to gain a full outer shell, it needs to lose 2 electrons. So for that reason, calcium loses 2 electrons. Now that there is already 2 marks, because by understanding that calcium is losing electron, we get a mark. And by understanding the number of electrons it is going to lose, we get our second mark. So now we want to do the same with oxygen. And the electronic structure of oxygen was 2, 6. So its outer shell contained 6 electrons. So to get that full outer shell, and remember that 8 electrons represents a full outer shell in all but the most innermost shell, we're going to need to gain 2 electrons, aren't we, to get it up to 8. Of course, alternatively, we could lose 6 electrons, but that's going to be much more work for this oxygen atom than simply gaining 2, which is a much smaller number. So here we can say that oxygen is going to gain 2 electrons. So here we get another mark for stating that oxygen is gaining electrons, and our final mark for saying that it is gaining 2 electrons. So there we go, that there is our 4 marks. It's actually not as bad as it seems. And I would always say that it's all about using those key words. Don't feel like you need to be writing essays. Just get those keywords into your questions. So next up, we're asked to draw a dot and cross diagram of calcium oxide and show the outer electrons only. So whenever I'm asked to draw a dot and cross diagram, there's always one thing I want to start by narrowing down. There's 2 types of dot and cross diagram, and we need to make sure we know which one is relevant to this particular question. So there is the one with the square brackets and the little charges up above, and there's also the one with the overlapping circles, okay? Now those are completely correct in the right context, but there is a right and a wrong answer, dependent on what substance we're being asked to do the dot and cross diagram of. Because this first dot and cross diagram with the square brackets and the charges is for ionic structures, whereas this second one with the overlapping circles we use for covalent structures. And to be able to identify whether what we have is an ionic or a covalent structure, you need to look at the elements that are composing it. So covalent structures are going to be made up of just nonmetals. So it could be nonmetals bonded to other nonmetals, but you'll just exclusively have nonmetals. So with ionic substances though, they are composed of a nonmetal and a metal. So if we go and look at calcium oxide, we know that the calcium is a metal, but the oxygen is a nonmetal. So you can see here that we are going to have to use the ionic dot and cross. And I think narrowing this down and not knowing that we really need to think about this is one of the number one ways in which we can make mistakes in these questions and go the wrong direction and not actually get any marks. So here, to do this dot and cross diagram, we can use our answer to part 1 of C. So for calcium, we knew that initially we had 2 electrons in the outer shell, but then we lost them, didn't we? And by losing 2 electrons, 2 negative things, we're going to form a positive ion, a 2+ ion. Don't forget that electrons are negative things. Imagine you have lots of negative thoughts and you get rid of them, you feel really positive, don't you? Just like this calcium ion will be too. And this again is another very, very common mistake that people make. The thought of losing something, you think, oh, that's negative, so it should be a negative charge. But no, you're losing negative particles, which actually makes it positively charged. So the calcium ion will just look like this. We'll just do an empty circle because we've lost those 2 electrons, and then now we have a 2+ charge. Over on the oxygen, on the other hand, we know that it did have 6 electrons in its outer shell, but then it ended up gaining 2 electrons over from the calcium. So I'm going to do 2 circles, and of course instead you could have done 6 dots and 2 crosses. It works out exactly the same, so don't worry. So we've gained 2 electrons, which means that we've gained 2 negative things, which makes us 2- charged. So that there is our dot and cross diagram of calcium oxide. Perfect. Here we're told that the solution of copper 2 sulfate was electrolyzed using 2 copper electrodes. This process was carried out at different currents, so we did it at 0.1 amps, 0.2 amps, 0.3 amps, and 0.4 amps. The mass of the anode and the cathode were measured using a balance before and after the electrolysis. Results were recorded in the table below. So here we're asked to describe the results in the table. And you can see it's a 3-mark question. So we need 3 good points in our description. So starting off, let's have a look at the mass of the anode before and after electrolysis. So if I look at it, I can see that it started at 20 grams to begin with, but in every different current there, you can see that the mass has gone down. So the first thing that we can say is that the mass of the anode decreases after electrolysis, and that gets us our first mark. So the next thing to think about, let's do similar, but this time for the cathode. You can see that all of the cathodes start with a mass of 20 grams, but then after electrolysis, this time, you can see that they all go up. So they all gain mass. So the second mark we can get here is that the mass of the cathode increases after electrolysis. So now we need to have a look at the bigger picture of this experiment. And we haven't really talked about how current affects things yet. But you can see that as that mass of the anode is going to decrease, you can see that as the current gets bigger, that decrease gets bigger. And the same with the cathode. The mass of that increases, but that increase gets bigger as the current increases. So the final thing we can say is that the change in mass increases as the current increases. And just to make sure that you can really clearly see that, of course, when we have 0.1 amps, it goes from 20 to 20.05, so it has increased by 0.05. Whereas when it's 0.2 amps, I can see it increases by 0.08. 3 amps, I can see it increases by 0.18. And finally, at 0.4 amps, I can see that it's increased by 0.31. So I can certainly say that the change in the mass increases as the current increases. So now we're asked to explain the results in the table. Because this is an explain question, we need to give the chemistry behind why this happened. So first, let's have a think about that cathode, where we know that the cathode ended up increasing in mass. So the copper ions end up getting reduced at the cathode. And when they get reduced, they gain electrons and form copper atoms. And by forming copper atoms, that is what's going to cause that increase in mass, because we have made atoms. So let's have a think. We don't have to include this in the answer, but it's helpful for us to visualize it. Let's remind ourselves of the half equation that goes with this. So the copper ions, which are going to be Cu2+, get reduced, which means that they are going to gain electrons and end up forming copper atoms. Now that sort of sums up what we've said, but in an equation. So I think just to help you understand it and to link it with those half equations, it's helpful to write it down. So now we have the other side over at the anode. So at the anode, the copper atoms end up being oxidized, so they lose electrons, forming copper ions, and therefore going into the solution. Now that leads to this decrease in mass, because whereas we had atoms, we don't have them after this oxidation. So let's look at the half equation, just to link this with the half equation side, of course. So we've got copper goes to copper 2+ ions plus 2 electrons. And that is the reason why we get a decrease in mass at the anode. So quite a challenging question, I think, but hopefully that's clear. Now we're asked to calculate the percentage increase in mass of the cathode when we use a 0.4 amp current. So let's remind ourselves of these results from the previous question. We're just looking here at the 0.4 amp current and the cathodes increase in mass. So let's remind ourselves now of that equation for percentage increase, because of course we need that, don't we? Percentage increase is going to be equal to the increase or the difference between the values divided by the original value where we started from, and then we times it by 100 to make that percentage. So in this case, we want 20.31 minus 20.00 divided by that original mass of 20.00, then we times it by 100. Putting this into our calculator, I end up finding it to be 1.55%. And there's our answer. So next up, we're told that beneath the copper anode, a sludge builds up. Just looks like a little mucky substance underneath that anode. Here we're asked to suggest an explanation for the presence of this sludge. And it's a suggest question, so we don't necessarily know this. We haven't necessarily learnt this in class, but we need to have a good stab at it. And here the suggestion is that maybe that copper anode wasn't pure. Maybe it actually had some impurities within it. So when that electrolysis takes place, the copper ions and the copper atoms are taking part in the process. But any impurities just end up dropping down underneath that anode and creating this sludge. The copper produced in this electrolysis can be used in the following reaction to make copper sulfate. So here we've got copper plus 2 sulfuric acids makes copper sulfate, SO2 and H2O. Here we're asked to calculate the mass of sulfuric acid required to fully react with 20 grams of copper. Now this question is a reacting masses question. And the idea is that if we can work out the number of moles of one substance within that balanced equation, we can work out the moles of anything in that equation and use that, therefore, to work out their mass. So to work this out, I'm going to start by rewriting that equation along the top of the page. So I'm just going to write that copper plus 2 H2SO4 goes to copper sulfate plus SO2 plus 2 H2O. And then I would go back and read the question, okay? And I can see that this question, it talks about the mass of sulfuric acid and copper. So I'm just going to circle those two and just ignore everything else in this question. And then I'm going to write a few different rows. I've got mass, MR, and moles. And what the idea is, in how I like to organise this, is I can put all the information in the right slot, and then I'm not going to try and figure out where it is halfway through the question. So I know that there's 20 grams of copper. I know that the MR of sulfuric acid is 98. And from the periodic table, I can see that copper has an MR of 63.5. So because I got 2 out of 3 in that copper column, I can work out the moles of copper. I know that moles is worked out by using mass over MR. So if I just substitute the values I have in that column for copper into this, and do 20 divided by 63.5, I get the moles of copper. So I know that the moles of copper is 0.315. And I like to fill that in into my little table as well. Next up, if we look at the number of moles of copper to sulfuric acid, you can see that it's actually a 1:2 ratio. Now that means that now that we've got the moles of copper, we just know that we have double the moles of sulfuric acid. So sulfuric acid moles is equal to 2 times by 0.315. It means that the moles of sulfuric acid equals 0.630. So now again, if we look at that column for sulfuric acid, we just got one thing missing again, and we've got 2 other things. That means we can go back to our equation. And we're going to use it in this rearranged form that mass is Mr. Moles, MR times moles. So 98 times 0.630 ends up giving us the mass of sulfuric acid of 61.74 grams. And that is the solution. And I would really recommend this idea of using this little table to organise the information in any of these reacting masses questions, because it's a great way to organise your information so you feel a little less confused. The electrolysis of copper sulfate can also be carried out using inert electrodes, for example, graphite or platinum. So here you can see we've got a little diagram of us doing it all again, but this time instead we have graphite cathodes. Now we're going to name another property that the electrodes must have in addition to being inert for them to be used in electrolysis. Now, quite simply, they need to be conductors of electricity. Otherwise, nothing is going to happen in this reaction because they need to be there to complete the circuit. So that is our answer to part F. Now we're asked to write down the half equation of the reaction occurring at the graphite cathode. So the graphite cathode is the negatively charged electrode, which means that the copper ions are going to be attracted to it and they're going to gain electrons from it. So in this case, the copper ions are going to be reduced by the copper ions and turned into copper. And so that means that our half equation is copper 2 plus 2 electrons to balance with the 2 plus charge of the copper ion makes copper. Here we're told that a gas is formed at the anode. The student carried out a test and identified it to be oxygen. The volume of oxygen evolved was measured and used to calculate the mass of oxygen produced using the electrolysis of copper sulfate. We're told here that the mass of oxygen produced is equal to 0.003 grams. Here we're asked to calculate the number of atoms of oxygen produced during this electrolysis of copper sulfate. So whenever we need to get the number of atoms, we need to remember that's not the same as the number of moles. But if we get the moles, we can use that to work out the atoms, okay? So here, as we know the mass of oxygen gas produced, we can use that to work out the moles of oxygen gas by using the fact that moles is equal to the mass over the MR. Now, what we need to remember is that that is the moles of oxygen gas, which is O2. It isn't the moles of O's or anything like that, no. It's the moles of oxygen gas that we've got there. So as a result, when we use the MR, we don't just want to look at the periodic table, see that oxygen's 16, and then write that down. No, what we want is to work out the MR of O2. So the MR of that, O2, is going to be 2 times that 16, which gives us 32. So substituting this into our moles equation, we end up having the mass of oxygen is 0.003 divided by 32. Putting that into the calculator, we end up getting 0.0009375. So that is our moles of oxygen gas. Now we can work out the number of molecules of oxygen gas by simply timesing this by Avogadro's constant. So if we take those moles of molecules and then times it by Avogadro's constant, we end up finding that we have 5.64375 times 10 to the 20 molecules of oxygen. However, it would be very easy to stop there and we would still have 2 out of 3 marks. But if we go back and look at the question and see we actually want the number of atoms of oxygen produced. Now, if you look at the formula for O2, you can see that for every 1 molecule of O2, you have 2 atoms. So in this case, the number of atoms of oxygen is just going to be 2 times those number of molecules that we just found. And that's going to give us our final answer, which is 1.12875 times 10 to the 20. And of course, we can round that. The question hasn't specified how to round, so you don't need to leave that full answer. You can round it, and I'll probably do that here. I'm going to call it 1.13 times 10 to the 20, doing it to 2 decimal places. But so long as you round that correctly or leave it as it is, you'll have your full marks for part H.
So here we're told that the reaction of sodium carbonate with ethanoic acid is an example of an endothermic reaction. Now this isn't a specific reaction we should be familiar with or anything, they're just giving us all the knowledge about it right here in this question. So a method used to investigate the temperature change when 10 grams of sodium carbonate is added to 50 centimetres cubed of ethanoic acid is 1. We will place a polystyrene cup inside a glass beaker. 2. We will measure 50 centimetre cubed of ethanoic acid and place it in the cup. 3. We will measure 10 grams of sodium carbonate. 4. We will put a thermometer in the cup. 5. We will record the temperature of the ethanoic acid. 6. We add the sodium carbonate to the cup. 7. We will give it a stir. And 8. We will record the highest and the lowest temperature reached by the solution. So here we're asked to give 2 ways that the method could be changed to improve the accuracy of the results. So there's a few different ways we could do this. We could add a lid to prevent heat loss to the surroundings. We could repeat this experiment and calculate a mean for it. We could also look a bit more at the apparatus and maybe use a more accurate thermometer, for instance, a digital thermometer. Now, we haven't got too much information about that previously, so it might be a suitable suggestion there. And another thing we could do after that is maybe we can use a more accurate balance, because we know we were just measuring 10 grams of sodium carbonate. What instead if we tried to measure 10.0 grams or 10.00 grams? That would indeed be more accurate. So there are 4 suggestions of things you could say to increase the accuracy of the results. Any 2 of those will be what you need to get your marks. So now we're asked to suggest why a polystyrene cup was used. Polystyrene is an insulating material. So by using that rather than glass, for instance, we will end up reducing the heat loss to the surroundings, ensuring that more of that heat is going to be used to heat up our mixture, which we can then measure its temperature using a thermometer. So our answer to this, the reason why we use a polystyrene cup, was to reduce heat loss to the surroundings. So now we're asked to explain what is meant by an endothermic reaction. So this is a great definition to learn if you don't already know it. So an endothermic reaction is a reaction that takes in energy from the surroundings. And a common implication of that is that your temperature of the surroundings is going to go down. And so we will see an actual decrease in our measured temperature. So there you are. Endothermic reaction is a reaction which takes in energy from the surroundings, whereas an exothermic reaction will be one that gives out heat to the surroundings. As a little extra tip, here is a useful way to think about it to help you remember which one is which. So let us have a think about the word endothermic. So that's got 2 parts to it. It's got endo and thermic. Now endo is a bit like in or into. Whereas if we now think about the word thermic or therm, we can think thermometer or thermals and things like that. And that refers to heat. So when we have the word endothermic, that's all about taking in heat or taking in heat energy. Because now if we think about the word exothermic, then the exo bit, I think it's fair to say that sounds a little bit like exit. It's got that same stem of the word. And so exo refers to like exiting or going out. And the thermic part of the word, again, it still means heat. So here, when we want to define what exothermic is, we can say that it gives out heat energy this time. So that's a useful way to distinguish between the 2 of them. So here we're asked to complete the enthalpy profile diagram for an endothermic reaction, like that one observed between the calcium carbonate and ethanoic acid. And here we're asked to label the activation energy. So here, because this is an endothermic reaction and it takes in energy, the products are going to have more energy than the reactants because it took in energy. So if we label this now, we're going to have the reactants over at the beginning of the progress of this reaction. And then we'll have the products afterwards, but they're going to be slightly elevated compared to the reactants because the products are there as a consequence of the reactants taking in energy. So now we need to do our little bump. And so starting from the reactants, we're going to do a curve which goes above the products but then ends on the products. And the activation energy is the height of that curve. So right from the reactants at the bottom of it up to its peak. That there is what the activation energy is. And that there will be all of our marks in here. We're going to get 1 mark for showing the products line above the reactant line, and we're going to get another line for the activation energy drawn correctly and labelled on our diagram.
So in this question, we're told that diamond and graphite are allotropes of carbon. And what an allotrope is something which is made of the same atom, but it's just arranged in a different structure to form something slightly different. So here we've got diamond and graphite, both made up exclusively of carbon. So we're given a table with their properties. We're told that diamond doesn't conduct electricity. It has a very high melting point of 4,000 degrees C, and it is very hard. Whereas graphite is a good conductor of electricity, a lower melting point of 3,600, and it is soft. So some very different properties there. Now these 6 markers are a little bit different to a normal question. Because with a normal question, you would think, oh, it's a 2 marker or a 3 marker. You need to give that many marking points. You need to say that many significant things to get those marks. And here, although this is a 6 marker, certainly giving 6 points would be good. That isn't necessarily what's going to get you the marks. Because if you gave 6 marks about diamond, you probably wouldn't actually get many marks. Because what these 6 markers are looking for is they want you to give a high level of detail and talk about all relevant points. You want to give a full answer discussing a bit of everything, nicely balanced. But you're not necessarily going to get it for just six facts that you lay out that's relevant. It has to answer the question fully to a high level of detail. So let's have a look at how I would suggest answering this question. So here I'm going to start talking about diamond, and I'm going to discuss the structure and properties that diamond has that makes it distinctive and special, and then we'll link it to its properties. So in diamond, every one of its carbon atoms forms 4 strong covalent bonds to other carbon atoms. Now, that is very, very distinctive of the carbon atoms in diamond. So now we've talked about the bonding, let's mention the type of structure that diamond has. So diamond has a giant covalent structure. So let's link all this now to the properties. So we've said, haven't we, that diamond has a very high melting point of 4,000 degrees C, and it is also very hard. So we need to describe why it has those properties and how it links to what we've said about the bonding and structure. So the reason why it has that very high melting point and it's very hard is because of those strong covalent bonds. It is going to take a lot of energy to overcome those bonds and to break those bonds. That is going to have a direct impact on this high melting point and it being very hard. So the next thing that we want to talk about here is why is it that it doesn't conduct electricity? Well, if we look at each carbon atom would normally have 4 electrons that it could donate to form bonds, and every single one of those does form bonds because it has 4 strong covalent bonds. As a result, there's no spare electrons, there's no delocalized electrons that would be what's needed to conduct electricity. So that's why diamond doesn't conduct. Let's get on to graphite. So in graphite, each carbon atom only forms 3 of these strong covalent bonds. So it doesn't form the 4 that diamond did. And that's one of the main differences between diamond and graphite. So if you're not 100% familiar with those differences, then I would definitely recommend that you make yourself a little flashcard with a nice table comparing the two. So graphite, we've mentioned that each carbon forms only 3 strong covalent bonds, now we can link it to the properties of graphite. So we can see in the table that there's a lower melting point for graphite, and it's also soft. And the reason for that is that graphite forms layers. And those layers, they don't have these strong covalent bonds between them. They've only got weak intermolecular forces. And as a result of these weak intermolecular forces, it's going to be really quite easy to overcome these forces. And so for that reason, we don't have as many strong bonds to break. We've got some that are actually quite weak. And then we have that knock-on effect there of that lowering the melting point and making it softer. So then the final thing really to mention about the properties of graphite is going to be about the fact that it is a good conductor of electricity. So if we think back to the fact it only forms 3 strong covalent bonds, and carbon, of course, it has 4 electrons in its outer shell. So if only 3 of those has gone to form covalent bonds, then we're going to have 1 left. And that one that's left is delocalized, which means that it is going to be free to move through the layers that are formed in graphite, and it can carry that charge. And that there is what's required for something to conduct electricity. So that is why graphite is a conductor of electricity, because it has a delocalized electron which is free to move through the layers. So let's just look at some of the key facts that's important to know about diamond and graphite, the key words that are going to bring you in the marks in an exam. So for diamond, knowing that you have 4 strong covalent bonds, that you have a giant structure, and then for graphite, that we only have 3 strong covalent bonds and that we have layers formed. Also, the fact that graphite has 1 delocalized electron for every carbon, and in diamond, you actually have no delocalized electrons. If we were to strip back everything here that we have said, those are the key facts that you can link to anything if you learn those. So I'd really recommend that you learn those key facts. Draw up a nice little table in your notes to compare diamond and graphite and get learning it. And it will really impact you because these questions always come up in the exam. Another allotrope of carbon is Buckminster fullerene, shown below. Buckminster fullerene has a low melting point and is slippery. Here we're asked to explain why. Well, firstly, it's important that we remember that Buckminster fullerene is a molecule, and therefore we're going to have weak intermolecular forces between these molecules. Now, because they're so weak, it only takes a little bit of energy to overcome them. And that's where we end up having this low melting point and this slippery substance. Because due to the fact that we have these weak intermolecular forces, we only need a little bit of energy to overcome them. And that there will be how we get our 2 marks. Paper chromatography can be used to identify the presence of different dyes. The chromatogram below shows the results of an experiment to investigate the composition of different inks. Spots of ink are placed on a pencil line using a pipette. Here we're asked to identify the stationary phase used. Now this is another one of those little facts that we're expected to know. So paper chromatography uses the stationary phase of simply paper. And by stationary phase, literally we mean what is the component of this chromatography which remains stationary. Now that is the paper, because the paper just stays there while the mobile phase moves through the paper. Okay? That brings us on to the next part where we're asked to identify the mobile phase used. Now the mobile phase is a solvent. Of course, you could give an example of a solvent here, or you could simply say water. All of those would still give us our mark. But what happens here is the solvent is mobile in the chromatography. You will place the stationary phase in the solvent, and the solvent will almost get soaked up through the stationary phase of that paper and move, taking the dissolved dyes in it. And that is how we get all of these different spots arising on the paper. Next up, we're asked to suggest why a pencil line is used rather than a pen line. Well, the explanation here comes from the fact that if we drew on a pen line, then that pen line would also dissolve in the solvent. And as a result, it's going to run and ruin our results. Whereas a pencil line will not dissolve and we won't get this problem. So that's why we use a pencil line. The table below shows the RF values for some different dyes. So we've got blue, red, yellow. And in this question, part D, we're asked to identify the dye in sample X and to show how we find our answer. So first things first, let's remind ourselves of the formula for the RF value. So the RF value is calculated by taking the distance moved by the dye or whatever substance we're looking at and dividing it by the distance moved by the solvent. So that means we need to get our rulers out, okay? And we need to measure the distance from the pencil line to that dot in the X column, okay? So we're going to get our rulers out and measure that distance. And we're also going to measure the distance from the pencil line again up to the solvent front. Now, don't worry if you think, oh, if I'm measuring this on a screen right now or on paper or I've half-sized it on the printing, because this is a ratio, it doesn't actually matter your measurements exactly. Your RF value will still come out as 0.2 or thereabouts, okay? So just take each measurement and you'll notice you will get 0.2 or at least very close. Now that means that you're going to say that blue is the dye here. And that's your answer. So next we're asked to explain how chromatography can be used to determine if a substance is pure or impure. Now here we will say that pure substances will only produce one spot on the chromatogram. However, an impure substance will show two or more different spots on the chromatogram. And that's how we can distinguish between a pure or an impure substance. So just to recap, to get those 2 marks, chromatography can be used to determine if a substance is pure by seeing only one spot and impure if there are 2 or more spots on the chromatogram. Good work. A different type of chromatography called gas chromatography can be used to test blood samples for the presence of drugs. Here we're asked to describe how different chemicals present in a blood sample are separated using gas chromatography. So what happens is gas chromatography is your sample gets vaporized so that it becomes a gas. But then different chemicals within that gaseous sample are going to travel at different speeds. They're not all going to travel at the exact same speed. They're going to travel different speeds. And then as a result, when it comes to the detector at the end of this, they're going to leave our gas chromatography machine at different times and get detected at different times. Now, this amount of time it takes in the machine is called the retention time, and that is what we use in gas chromatography instead of RF values in the paper chromatography. So here, just to summarize and recap, the way in which different chemicals in a sample will be separated using gas chromatography is using the fact that different chemicals will travel at different speeds and therefore they will leave the machine at different times. And that there will give us our 2 marks. During this process, a gas chromatogram is produced. And here we've got a diagram of one here. We can see we've got abundance on the y-axis and retention time on the x-axis. Here we're asked to describe what can be deduced from the gas chromatogram above. So here I can see we have got A, B and C. The fact that we've got 3 distinct different peaks tells us that 3 substances are present in this sample. And that's the first thing that we can say. Another thing that we can say is that out of these, C is the most abundant. If you look at its peak, you can see its peak is much larger than the others. Now finally, A and B, you can see they both peak at the same point. And for that reason, we can say that equal amounts of A and B are present in this sample. And that would be our analysis of this. Now this question, you can see it's only a 2-mark question. So we only actually have to say 2 of those points to get the full marks. So if you can understand all 3, brilliant, you can definitely get full marks in this question.
Well done for making it all the way to the end of the paper. I'm really, really proud of your hard work. If you're watching this just before chemistry paper 1, then good luck in your exams. Otherwise, give yourself a bit of a break and then we can start physics revision.